Hi everyone, good afternoon. Uh, the title of my talk is Quantum Mechanical Analysis of Polarization of Light Beam. It was my BSc project here under the guidance of Dr. Shovan Kumar Sunda. Since it is UG symposium, so I thought I should go for my UG project. And this work actually is a review work which is based on the work of Professor Mohit Lahiri and M.A. Lul on the quantum mechanical analysis of dynamical optical experiment. Uh, so let's begin. This is moreover the plan of my talk, and if we consider an electromagnetic beam propagating along positive z direction, and the two mutually orthogonal components ext and uyt, which is perpendicular to the propagation axis, uh, the polarization matrix is defined to characterize correlation properties between the orthogonal components of electric fields. Now, since we are searching for the quantum mechanical analysis, we should quantize the electric field. So basically, it is a algebraic thing and the quantization and quantum field theory thing. So the result, the final result, the quantized electric field can be represented as this form. Here, the first term is the positive frequency part, which corresponds to the annihilation of photon, and the second term is the negative frequency part, which corresponds to the creation of photon. And k is the wave vector which satisfies these relations. Now, let's say the field initially is in a state I. If this field makes a transition from this initial state to a final state F, in which one photon is being polarized in the mu direction, then the matrix element takes the form of this. So, the probability per unit time that a photon be absorbed by an ideal detector at point R at time t, that is proportional to the summation of the all final states, which has the form of this. So the first order correlation properties of the fields are specified by the correlation matrix, which is defined as G1 RT and this trace of density operator into E minus E and E plus. Mu and nu label the mutually orthogonal components. Here these are X and Y. So let's move to the canonical experiment. Classically, if a light beam is considered passing through a compensator and followed by a polarizer, then the intensity of the beam emerges from the whole system will be like this, where Jxx, Jxy, Jyx and Jyy are the classical polarization matrix element, and theta is the polarization angle, and delta is the phase difference between two components, ext and uy. Similarly, there is a similar canonical experiment. They have in quantum mechanics. The only difference is that there is a photodetector placed just behind the polarizer to detect the photons. So beam emerging from the polarizer is linearly polarized and it makes an angle theta with the positive x-axis, let's say. So this theta is the polarization angle, and so the average counting rate of the photodetector can be written like in terms of the polarization matrix elements. This was the whole setup. So now the determination of matrix element. So we can determine the matrix element by changing the theta delta values. So for a certain set of theta delta values, from this expression, we can get the classical polarization matrix element like this. And similarly, for the quantum mechanical case, we can get the polarization matrix element like this. So let's move to the correlation coefficient. The correlation coefficients are basically defined by normalizing the polarization matrix, and it has the form of this in terms of the polarization matrix elements. And the polarization matrix satisfies these properties, where it tells that the polarization matrix is always non-negative, definite, and Hermitian, and from the causes towards inequality. And since the determinant of the polarization matrix is greater or equals to 0, we get the modulus of correlation coefficient is lies between 0 and 1, and it has the extreme two values 0 and 1. When the correlation coefficient is 0, so that means this has the complete absence of correlation, and when it is 1, it has the complete correlation, and when it lies between 0 and 1, it has a partial correlation. Now, if we consider an unpolarized light, that means for the classical case intensity, and for the quantum mechanical case the detection rate is independent of phase delays and polarization angle. Theta and delta both are 0. So for that case, the correlation coefficient is 0, and hence the diagonal elements of polarization matrix are equal, and the off diagonal elements are 0. That means the polarization matrix for unpolarized light is proportional to unit matrix. Now, completely polarized and partially polarized light. The way we can call the beam as completely polarized when the correlation coefficient is 1, and the determinant of polarization matrix should be 0 for completely polarized light, and when the correlation coefficient lies between 0 and 1, that means the light is called partially polarized. So from that, it can be said that when we pass through a partially polarized light, then we can get the two parts. One is completely unpolarized, and one will be completely polarized. Now, the degree of polarization, which says about the states of the polarization of the beam. So, classically, the degree of polarization is defined as the ratio of intensity of polarized light and the total intensity of the beam. And for quantum mechanical case, the degree of polarization is defined as the ratio of counting rate of photodetector for polarized light and the total counting rate. So, by doing the algebra, we get the formula for DOP as this, which is dependent on the determinant of polarization matrix and trace of the polarization matrix. Now, when the degree of polarization, it is of course also from Cauchy-Schwarz inequality. It also has two extreme values, 0 and 1. When it is 0, the beam is unpolarized, and when it is 1, it is completely polarized. And when it lies between 0 and 1, it is partially polarized. Conclusion is that the main thing is the techniques we generally used in classical optics can be applied in quantum theory. And the difference is that in classical case, the time averages have been considered, and in quantum mechanical case, the expectation values have been considered. And the polarization property of classical light can be analyzed by the quantum analysis, but the converse can't be possible. Actually, when the classical analysis has been done, it was done for the statistically stationary light beams, but it has no there is no valid proof that this can be done for statistically. This can be done for the beam which are not statistically stationary, but quantum thing can be done for the cases for the fields which are statistically not stationary. So that is it. These are the references. Thank you.
My question was polarized light.
Yes.
If light is propagated in any direction, and the electric field and the magnetic field is also perpendicular to the propagation of the light. And if we polarize this light, that means by means of polarization, its propagation should be in one plane.
Okay. Yes.
So which plane? Which plane? Electric field का plane क्या magnetic field का plane इसको हम suspend कर रहे हैं propagation होने के लिए.
We have considered here the electric field things.
Electric field को अगर suspend किया जाए propagation होने के लिए तो फिर तो light ही नहीं रहेगा क्योंकि light तो electromagnetic.
I am not getting your point. I mean, what is the question? Is it field?
Light.
Okay, yes,
Light is
you have calculated all these things considering only the electric field.
Yes.
Why you are not using magnetic field in your calculation? Why you are only but not considering?
Will not get any photon.
No,
We can't.
he is talking. Can you do these kinds of calculations involving the magnetic field? That's what his question.
Is instead of the electric field, the magnetic field is being polarized.
Why you are not using magnetic field in your calculation? There is some reason.
Our main goal is to detect the photons,
Yes.
right?
Yes.
So that's why we are considering the electric field here.
So magnetic field, why magnetic field has no issue here? I think magnetic field will not
Contribute to the photon detection. Yes.
That's why so I have one question. We have one slide. You have talked about ideal detector.
Yes.
So what is it that
Ideal detectors means actually the detector size is in the atomic size, and it detects the E minus and E plus in both in the same time and same place. I mean R and T are the same. For
how you can measure this calculations you have done? So is there any experimental verification? How you can visualize the ideal detector?
that I have no idea.
You talked about statistically stationary waves.
Yes.
So what do you mean by that?
Statistically stationary beams means the statistical properties of beam, like intensity or someone that doesn't change with time.
Any more questions?
What is the use of the compensator between source and Oh, it creates the phase delays between the two components. Is there any effect if we don't? If the octagonal components, then you are, no, I don't think so. So octagonal components are basically the complex conjugate to each other. If you don't consider the phase delays, then the complete matrix will not be Hermitian then. Yes, that is the reason.
Normal, there are two types of particles.
You already asked the question. When you have the look like. Please go ahead.
So there are massive particles and non-massive massless particles. So normally massive particles shows electricity, but massless particles shows polarization like gluons and photons. Is there a connection?
They have studied here the quantum mechanical analysis of, they try to detect the photons, right? So I don't know. Maybe.
Yeah. In the properties of polarization matrix, we have just slide. So we have written these properties of this, and then you have calculated the correlation coefficient, something like that. So
Yes.
how will you go to that from this correlation coefficient? How you calculate that? This.
Correlation coefficient is basically defined.
Okay.
This is the correlation coefficient, and that is normalized with some phase factor, and then we get.
Yeah, how you get that? How this problem?
That is from the from this average counting rate we can get. Since the polarization, this see, here is a these properties are there. So from using these properties and we can get the correlation coefficient. And I have calculated using these properties from the counting rate.
What is the one denotes first order?
One denotes the first order correlation properties.
Answer, so we can not have any more question. And with this, we mark the end of our theoretical session. Thank you.